Okay, the future of commercial aviation. This particular aircraft, albeit is very interesting, and I think it's pretty sleek looking. It doesn't appear that it's going to get off the ground because it was originally developed by Boeing, or planned by Boeing, to be a subsonic cruiser. And I say subsonic because it was almost supersonic at 0.98 Mach. The thing is that they decided that it was not very fuel efficient, and so they were developing, of course, have been developing the 787 Dreamliner. So where is subsonic commercial travel going? They're going to have more of these blended wing bodies, and we'll show you some examples in just a second. Engines mounted above the wings for noise shielding. This is both for subsonic and supersonic type aircraft. Embedded engines using variable area nozzles, thrust vectoring, noise shielding, that sort of thing. Boxed and joined wing configurations. Hybrid aircraft that fly on gas and battery power. And, of course, there's going to be challenges. A lot of noise issues, fuel efficiency problems, emissions issues with carbon dioxide and various nitric oxide mixes. And that's going to drive more and more of this telecommunications. And they have this what's called access grid technology that is advanced video conferencing that includes huge displays and with multiple simultaneous operating cameras at both sites on the nodes. And scientists and companies will continue to research, of course, and develop alternative biofuels for jet aircraft and also for turbojet aircraft. So these are some examples of future subsonic commercial aircraft. In the upper right-hand corner, you can see the wing body type design so that the fuselage is blended with the wing. And this particular project has variable nozzles and thrust vectoring for efficiency. The one on the left at the top is a NASA Lockheed Martin design, probably if it's going to come about somewhere in the year 2020. And this is a kind of a boxed or joined wing. And if you see up here, maybe you can't see very well, but you see how the wing tips are joined with the horizontal stabilizer in the back on the tail. Can you see that? So that is the joined wing concept, and that's for better fuel efficiency. And then more of the blended body with Boeing, again about the same time frame of development. And then here in the lower left is a double cabin type thing, about 180 passenger, what they call a double bubble configuration. And then here's one of the examples of the hybrid I was telling you about, the twin engine gas and battery power aircraft that NASA and Boeing are developing. What about supersonic commercial travel? Well, once again, the engines are going to be mounted above the wings probably to shield more ground noise. Again, you're going to have designs for improved airflow to control the sonic boom. As you know, the supersonic Concorde was not allowed to fly over U.S. air soil because of the supersonic, because of the noise, because of the sonic boom. Aircraft with variable cycle engines, aircraft incorporating multiple engine types with various flight phases and long-range flight in supersonic and hypersonic regimes. High development cost is going to be a problem. Drag reduction challenges are going to be the wave drag. The wave drag is the shock wave that's formed across the surface of the wing and causes excess drag, and this occurs primarily in the range of 0.8 to 0.1, 0.2 Mach. You're going to have airfoil shape issues. Obviously, anytime you're extremely fast, you're going to have heat issues. And again, we've got to reduce the noise of the engines and the signature of the sonic boom from the shock waves. More powerful, fuel-efficient engines. Anytime you're developing shock waves and going faster, you've got to have more thrust to do so. And then, of course, multiple engine issues. I'll show you in just a second an example and take you on a flight of a different combination of engines to fly the aircraft. Here's some future supersonic and hypersonic commercial aircraft. Again, you see in the upper right-hand corner the Lockheed Martin design. And again, you can see a little better, I think, in this case, where you got this wing design hyperbolic shape, if you will, of the top of the back of the wing, and it helps with not only efficiency, but also supposed to control some of the shock wave effects so they're not so loud. And then here, and I'm going to give you an example in a second, this is the Zero Emission Hypersonic Transport, EADS. And then Boeing, somewhere in the year 2030, is looking at having an aircraft where you have a V-type shape tail section, and it uses the wings as a natural barrier for the sonic boom. You see the engines mounted over on top of the wing. You see the inlets right here and over here. So here's an example of that hypersonic transport I was telling you about. And there's three types of engines that are used in a sequence. First of all, you have the two low bypass turbojet engines they use essentially for takeoff and landing. And then you also have two small liquid oxygen powered booster rockets and a larger one that's going to propel the aircraft higher and faster. And then once you get up at altitude to go at speeds of Mach 4 and greater, you've got some hydrogen-fueled ramjets. So when you get back then to a point where you're going to be landing, then again, as I said, your turbo jets are going to be functioning for the landing of the aircraft.